Everyone. I will talk about our recent work published in TKDE, a high-performance index for real-time matrix retrieval. This is a joint work myself, Mingyu, Liang, Bingsheng, Zexin, Xia. We are from different universities, but the work uh, was mainly done when we were working at National University of Singapore. This is the outline of this presentation. First, I will talk about the motivation and background, and then I will elaborate some of the technical details of our proposed solutions, including challenges and the key ideas of our solution. And then I will present experimental results and the conclusion. Okay, why we want to do matrix retrieval? So these days there are many embedding techniques in machine learning. For example, word to vectors, image to vectors, and queries to vectors. As you can imagine, there are many objects can be converted to vectors. And many objects can be represented by matrix. Basically, a matrix is a set of vectors. For example, a document can be represented as a set of word vectors, where each word in document corresponds to a vector. A video can be seen as a set of image vectors. An audio stream can be considered as a set of finite lattice vectors. There are many applications which can generate these kind of vectors. For example, audio streaming platforms, including Facebook live streaming, Himalaya, Chinting FM. There are many these kind of audio streaming platforms. So this many of these applications they can be converted to matrix. For example, documents we can broken a document into a collection of words, and then we can use the word to vector technique to convert each word into a vector. Then all these words together forms a matrix, and this matrix corresponds to the original document. And if we have an audio, then we first divide this audio into a collection of images, and then we use image to vector to represent the video using a matrix. We can use an audio stream, represent an audio stream using a matrix as well. So similar techniques can be applied in other representation of objects. And these matrices are generated continuously. For example, Twitter, there are many short documents. And Facebook live audio generates a lot of audio streams, and YouTube live streaming generates a lot of video streams. And continuously generated contents need to be queried in real time in some applications. For example, users can use keywords for document retrieval, specifically like retrieving documents, short documents, or tweets from Twitter, or using image to retrieve videos, using sounds to retrieve audio streams, etc. So if we are able to provide the real-time support on this continuously generated data, then we can provide users more up-to-date content, which is streaming. Advantages of matrix representation. The first advantage is that we can design indexing and queries in a generic way. We don't need to design specific systems to support text or video or audios. If everything is represented by matrix, then we can design a system which support matrix retrievals, and basically we can and then on top of the matrix retrieval system, we can build many different applications. And this matrix representation can support more flexible similarity functions, for example, semantically similar in document retrieval, or uh, phonetically similar in audio retrieval, cynically similar in video retrievals, etc. And users can customize their queries. For example, some users may prefer newer objects, while other users may prefer popular objects. And then users can specify the ways of the popularity and the um, timestamps, and then the system um, can provide results to each individual users. And building such kind of matrix retrieval system can reduce development and engineering costs of building individual search engines specifically to each data type. Okay, so our solution, there are some challenges for building a algorithm for matrix retrieval. First of all, there are a large number of vectors. Because a vector, for example, 300 dimensional vectors, and each dimension can take many different values. So in combination, there are a large number of possible vectors, and we need to build an inverted index on these vectors to support the queries. If the inverted index is very large, then the query response could be very slow. And words and streams. So these are the inverted index. We often support stream matching, or is specifically used for text data. And the text can be sorted alphabetically. However, sorting vectors is not trivial. If we don't sort the vectors, then performing a sequential scan is too expensive. The key idea of our solutions, we propose a high-performance index equipped with both precise and fuzzy inverted lists. And the precise inverted list can be used to support exact matching, and some applications which need exact matching, then they can choose to use precise inverted lists. If users can tolerate some approximation, or they want to use approximate matching, they can choose to use fuzzy inverted list, which will speed up the indexing and query processing. We also propose a series of techniques to improve memory consumptions and efficiency. Specifically, we design hashing-based lookup for exact search, um, a vector to be stored in multiple inverted lists to boost efficiency, and store vector signatures instead of the whole vector to support fast similarity evaluation. The final key technique is we support index initialization to obtain more stable index. This is the overview of query processing and indexing on matrices. So when we are given the raw data, we convert the data into vectors, and then each object can be represented by a matrix. And that data set will correspond to a set of matrices. And then we build an index for this collection of matrices. And then when a user issue a query, we first convert the query into vectors, and then search on this inverted index. As a result, we can retrieve some matrices which are related to the user query, and then do some scoring and ranking, and finally we can represent the query results to our users. Our design is based on the log structure tree. So this LSM tree, so essentially it has multiple inverted index. The second inverted index is a row times larger than the previous inverted index, and there could be as many LSM tree inverted index uh, depending on the how big the problem is. And then the query will need to go through each individual inverted index to obtain the results. We have a technique to store a vector in one or multiple inverted lists. For example, in these first figures, one vector is stored in only one inverted list. So, for example, vector one, and which appears um, in this matrix, matrix 10, matrix 5, etc. And then each vector in the matrix is only stored in one place, in one inverted list. But we can also store one vectors in a matrix in multiple inverted lists to speed up the query processing. For example, this matrix ID of 10, and then we can store these vectors in the inverted list corresponding to vector 1 and corresponding to vector 2 as well, and many other inverted lists. And the reasons why one vector can be stored in multiple inverted lists is that the vector from the matrix may be similar to multiple vectors in the vector dictionary. So this duplication can speed up the query processing. Experiments to evaluate the performance of our proposed index. We use a relatively large dataset which contains 40,000 audio streams downloaded online. And then we convert the audio streams to vectors. In total, we have 16 million vectors, totaling to about 460 gigabytes storage in MongoDB. There are about 16 minutes per audio streams on average. In total, the audio streams is more than 1,000 hours. And we also transcribed the audio to text, and then the text contains about 16 million words on average. The number of unique words in each audio stream is about 400. And we use 16 dimension vectors for each word. And the dimensionality can be any numbers in our index, but in the experiments we use 13, because this is the common number to represent the audio phonetic lattice. The experiment was conducted on a machine running Linux with two Xeon 10 core CPUs, and the machine has 256 gigabytes of memory. This table shows the default parameters of the experiments, and more details are presented in our accepted papers as well. So the first comparison is against the existing approaches, including LSII and RTSI. So these vectors are proposed techniques. And we compare the query processing time on exact matching and also insertion efficiency on the precise inverted index. So as we can see, Vecdex is much more efficient than RTSI and LSII in terms of both query processing and insertion in this exact or precise inverted list scenario. And if we consider the fuzzy inverted list approach, we also have similar observations. Vectex is consistently outperform other techniques. And we also measure the dictionary size. As we can see, Vectex has much smaller dictionary compared with RDSI and LSII. And we also conduct experiments to study the efficiency of insertion. We vary existing vectors in the inverted index from 2 million vectors to 10 million vectors. In terms of the exact search, the efficiency is quite stable. So the insertion doesn't depend much on the index size because of the lookup. Lookup is based on the hashing, so we can find where to insert very quickly for the exact search. But for the approximate search, the time the larger inverted index will require more time. This is because when we are searching for the right place to insert the vectors, we need to perform more scanning. But in general, the exact search is more than 10 times faster than the approximate search. And we also the index size has insignificant impact on the cost of insertion, and the growth rate of the total time of insertion is stable for building index for exact search and approximate search. And we also conduct experiments varying the number of vectors to insert. As we can see, if we increase the number of vectors by 10 times, by 5 times, then the insertion time of the exact search is also increased by 5 times, almost linearly. And similarly for the approximate search. In terms of query answering, the time of query answering is about linear in the index size. This shows the number of vectors in the index, and as we can see, the time increases for both exact search and approximate search as the size of the inverted index grows. Similarly, if we increase the number of queries, the total query processing time increases. But they are relatively stable, and there is not a very significant increase in terms of query processing time. And we also propose to store the vector signatures instead of the whole vectors in the inverted list. And storing such signatures will have impact on the memory consumption and also the insertion time. In terms of insertion time, the approach of storing the whole vectors and storing the vector signatures is quite similar. This is because the majority of the time for insertion is on the index lookup on the vector dictionary. So the actual store of the vector or the vector signature takes a insignificant amount of time. But in terms of the memory consumption, vector signature-based approach is much more efficient compared to storing the whole vectors. This is because the signature we don't need to store much information, but the whole vector is much more memory consuming. And in terms of query processing using signatures, when the vector signatures are stored, As we can see, the efficiency improves notably. Um, and with the vector signatures, we can perform sortings on the inverted list, so that we can perform some prunings if the ordering information is obtained. As we can see, by sorting the vector signatures, we can further boost the query processing time. We also study the impact on insertions using multiple one vector stored in multiple inverted lists or single inverted list. As we can see, storing a vector in single inverted list is slightly more efficient compared to multiple lists. And in terms of memory consumptions, multiple inverted lists will consume more memory, so this is kind of obvious. But in terms of query processing, multiple inverted list approach is more efficient because we can directly obtain those results from different places and then combine them together. But using single inverted list, we need to perform more scanning. Because the use of approximation, different orders of insertion to the inverted index will result in a different inverted index. So our algorithm supports index initialization. So as we can see, if we perform index initialization, then the number of vectors in the index is more stable compared to the non-initialization approach. So if in total we only have 2 million vectors, the one without initialization, the inverted index is very, very small. But with index initialization, the size of the inverted list or the vector dictionary is more stable. So the number of vectors in dictionary of the index with initialization is larger than the one without initialization. This indicates that the important vectors are reserved in the dictionary when the index is initialized. So this functionality actually is quite useful. So if the users know which vectors is important, then they can store that in the dictionary rather than be represented by other vectors. We also study exact search using hashing. So as we can see, the number of vectors in the index, if we use hashing, the elapsed time actually is very very small compared to the exact search using nearest neighbor. So often hashing achieves 10 times speed up compared with using nearest neighbor search. Prunings and index update. So if we employ pruning when processing queries, we can notably improve the efficiency of the query processing. And the updates of our index can be done in just in a milliseconds level. So the index actually is very efficient to update. And we also conduct experiments to study when the threshold, the similarity threshold between two vectors varied. So if the threshold increases, the insertion time is increased as well. This is because the inverted index will become larger because the vectors tend to be different from each other if the similarity threshold is large. And in terms of the query processing time, they are quite similar, but in general, the higher similarity threshold results in faster query response time. This is because the pooling techniques will be more efficient. So this is also intuitive. The dictionary size would be larger if the similarity threshold increases. And we also conduct experiments on different dataset size. So we vary the number of queries from 800,000. We vary uh, the vectors from 800,000 to 20 million. So the query processing time, even for such a very large inverted index, the query can still be processing a few seconds. 1,100 queries can be processed in 5 seconds. And the insertion of 100,000 matrices to vectors takes only half an hour. So this is a very large number of matrices, and vectors can efficiently handle these insertions in just the level of minutes. Okay, in conclusion, we have proposed an index for real-time matrix retrieval. The index also supports real-time insertion with LSM3. Our proposed index supports both exact and approximate search, which many real-time applications rely on. We have proposed precise and fuzzy inverted index to power the index, and propose a series of novel techniques to achieve memory-friendly and real-time search. Experimental results show that our proposed index can support both the exact and approximate search on matrices in real time and is more time and memory efficient than the state-of-the-art methods. Okay, thank you very much for watching.